Hello everyone, my name is Caio dos Santos. I'm a teaching assistant 2 and a senior teaching assistant candidate. And today, let's talk about linear regression. And I will try to give you a bit of an introduction about this topic. And to do that, let's start with an example. And imagine you're working in a lab clinic, and each day you get like several patients, and one of them is doing his daily routine exams. And let's start with John. John is a 35-year-old man, weighs 90 kilos, and his HDL cholesterol is equal to 44. And after John, Susan comes up. Susan is a 55-year-old woman that weighs 75 kilos, and her HDL cholesterol is 40. After Susan, Anna comes up, and she is a 25-year-old woman that weighs 50 kilos, and her HDL cholesterol is equal to 60. David comes up. He is a 27-year-old man that weighs 72 kilos, and his HDL cholesterol is equal to 58. Claire is a 35-year-old woman that weighs 68 kilos, and her HDL cholesterol is equal to 50. And after Claire, Julia comes up. Julia is a 30-year-old woman that weighs 55 kilos, and we actually don't know her HDL cholesterol yet. And you might be thinking, would it be possible to predict her HDL cholesterol? Or would it be possible to try to find a HDL cholesterol that would be as close as possible to what her HDL cholesterol actual value is? And you might be thinking, how would all the previous patients help you with that question? And this is the question. So let's start talking about linear regression. And suppose there are two different variables, let's say HDL cholesterol and weight. And sometimes we search for some relationship between these two variables. We may be looking at the correlation between these two variables. We may be looking at the mean differences of these two variables, and so on. But let's take a look at the next graph for a second. And on the y-axis, you can see the HDL levels, and on the x-axis, you can see the weight. And each dot is actually a patient, right? And you might be thinking, is it possible to see some trend in it? Is it possible to look for some relationship between these two variables? I mean, how much would HDL levels vary with increases in weight, right? This is a very interesting question. So what if instead of looking at the correlation and the mean difference, we decide to see how would the HDL cholesterol vary with small changes in weight? And in order to do that, we must ask three questions. The first question is, as it is not possible to establish a perfect relationship between these two variables, how do we interpret the effect of other variables on the chosen dependent variables? For example, the HDL cholesterol. I mean, how do we interpret the effect of other variables that are not weight, right? And the second question is, what would be the best line, as we're talking about a linear regression, to fit in this relationship? And the third question is, how to be sure we are looking at only the effect of weight on HDL cholesterol? These are three very important questions that we must do before thinking about finding a linear regression model, okay? And let's start answering these questions with a simple equation, which is y equals a plus b times x plus e. Or we can rewrite this equation as HDL equals a plus b times weight plus e. And we already know what are the variables, the HDL and the weight, but we don't actually know what are a, b, and e. So a is the intercept of the model, b is the slope of the curve, and E are the residuals. We're gonna discuss more about them, like in sequence, okay? So let's just stop for a second. I know there's a lot of information here, and you might be a bit desperate because it's not an easy topic, but I'm gonna try to help you understand a bit more of this, okay? So what is an intercept? The intercept indicates the value of the dependent variable, in this case, the HDL cholesterol, when all the independent variables in the model are equal to 0. In this case, we actually have just one independent variable, which is weight. And in this case, it does not make much sense to assume weight equals 0. And this is important because for prediction purposes, the intercept is really important. But most of the times, it will not play an important part in the analysis, okay? Because what you're gonna be looking at is the slope of the curve. The slope of the curve can be seen as how much the dependent variable vary with a unit increase or decrease in the independent variables. In this case, how much the HDL cholesterol will change by 1 unit increase in weight. So the slope of the curve is actually showing the relationship between the dependent variable and the independent variable. And with that said, you can start estimating the model. We're gonna talk about the residuals in a bit, but let's just take a break here and we're gonna show you the output of a linear regression model. And in this case, we're using Stata, and don't worry about the math behind it because the statistical software will do it for you. And on the right picture, you can see the commands up there, the reg and HDL, which is your dependent variable, and the weight, which is your independent variable. And what you're going to be looking at is the coefficients of the variables. In this case, you can see the coefficient of weight, which is negative 0.63. And this value is actually your B, your slope of the curve. And the coefficient of the constant, which is 96.13, is your A, or your intercept of the model. And as you can see, the p-values of both the weight and the constant are equal to 0. So that means that both variables are statistically significant in this model. On the left picture, you can see the graph that we saw before. And now you can see the fitted values. And these fitted values are the expected levels of HDL we get from our calculated equation using every single value of weight we have in here, okay? So for instance, for a weight equals 60, you'll have an expected value for HDL. For a weight of 80 kilos, you'll have a different expected value of HDL. And with that, you can write your equation, right? So our equation is HDL equals 96.13 minus 0.63 times weight. And with that, we can go back to our patient, Julia, to actually calculate her expected HDL cholesterol level, right? Because we have her weight. So if you replace the weight in the equation, you will end up with an HDL level of 61.48. And you must recall that this is not the actual value. This is just the expected value, okay? And is that different? Let me show you. We can use all other patients to see if the expected and the actual values are the same or if they are different. So John was a 90 kilos man, and his HDL level was 44. But using our linear regression, you will end up with an expected HDL level of 39.43. And you can see that they are not the same, but we can keep going. And Susan, her expected HDL level was 48.88 versus her actual value, which is 40. Anna had an expected HDL level of 58.33 versus her actual value of 60. David had an expected value of 50.77 versus his actual value of 58. And Claire had her expected HDL level of 53.29 versus her actual value of 50. And the thing is, you already saw that they are different, but you're thinking, why is there? Why is that? Why there is this difference? And this difference actually helps you understand what are the residuals of the model, right? So the residuals are the difference between the actual values and the predicted values. In a way, this difference is capturing the effect of all other unobserved variables. And in this model, we are only using weight, but there are many other variables that affect the levels of HDL that we are not observing in this model. And the residuals are important to capture the effect of all other variables that are not observed in here, okay? And if you go back to the graph, you can see that the residuals are actually the difference between the actual value and the fitted values. And you can see that there are dots that are above or below the fitted values. So there will be residuals that are positive and there will be residuals that are negative. And this is very important when estimating your model, because one very important assumption, which will be vital for you to calculate the values of the coefficients of A and B, is that the sum of the residuals has to be as close as possible to zero, okay? And when you maximize it, when you put these residuals as close as possible to zero, you're making sure that you're only looking at the effect of the observed independent variable on the dependent variable, all right? So this is why it is very important that the residuals are positive and negative, and if you sum them, you will end up with a value as close as possible to zero. But what is really important for us clinicians, researchers, is to understand why use a linear regression. And it is important to understand that a linear regression can be used to predict an outcome, as we did with Julia, and or to estimate an effect of an independent variable over a dependent variable, right? To look for the relationship between two variables. Thus, it is really important to critically think when selecting the independent variables in the model, okay? And a linear regression is also quite useful, especially in observational studies, when randomization process usually can be done, right? In such studies, like confounding can be a real problem, and controlling for a couple of variables is really important. And the linear regression is a tool for that, okay? So finally, you might be thinking how to build a good model. And there are a few points to consider when assessing a regression model. The first and most important, at least for me, is it is important that the model makes sense biologically. You can't just pick randomly some variables to put in the model. They need to make sense, okay? And second, as we already discussed, it is important that the model predicts with the minimum error as possible, right? And to do that, it is very important that the assumption of the expected value of the error is equal to 0. And another important point is a statistic called R squared. The R squared is a parameter that shows how much of the variability in the outcome that could be explained by the model. And theoretically, the R squared varies from 0 to 1, and the closer to 1, the greater the variability is explained. So in our example, our R squared was 0.5250. Thus, we can say that 52.50% of the variability of HDL is explained by our model, okay? And that is a lot. So it is often recommended to use the adjusted R-square because the more independent variables are added to the model, the greater the R-squared can be. So the adjusted R-squared penalizes adding more variables. Then a greater adjusted R-square means a better model, and that is one thing to look carefully. All right, and I hope you enjoyed this brief introduction about linear regression. I'm always available to discuss more about it. I hope I have clarified some doubts about it and helped you a bit with this. And thank you for your attention.